Chapter 6. The Secret Life of Objects. An abstract data type is realized by writing a special kind of program, which defines the type in terms of the operations which can be performed on it. Barbara Liskov, Programming with Abstract Data Types. Chapter 4 introduced JavaScript's objects as containers that hold other data. In programming culture, object-oriented programming is a set of techniques that uses objects as a central principle of program organization. Though no one really agrees on its precise definition, object-oriented programming has shaped the design of many programming languages, including JavaScript. This chapter describes the way these ideas can be applied in JavaScript. Abstract data types. The main idea in object-oriented programming is to use objects, or rather types of objects, as the unit of program organization. Setting up a program as a number of strictly separated object types provides a way to think about its structure and thus to enforce some kind of discipline, preventing everything from becoming entangled. The way to do this is to think of objects somewhat like you'd think of an electric mixer or other consumer appliance. The people who design and assemble a mixer have to do specialized work requiring materials science and understanding of electricity. They cover all that up in a smooth plastic shell so that the people who only want to mix pancake batter don't have to worry about all that. They have to understand only the few knobs that the mixer can be operated with. Similarly, an abstract data type or object class is a subprogram that may contain arbitrarily complicated code but exposes a limited set of methods and properties that people working with it are supposed to use. This allows large programs to be built up out of a number of appliance types, limiting the degree to which these different parts are entangled by requiring them only to interact with each other in specific ways. If a program is found in one such object class, it can often be repaired or even completely rewritten without impacting the rest of the program. Even better, it may be possible to use object classes in multiple different programs, avoiding the need to recreate their functionality from scratch. You can think of JavaScript's built-in data structures, such as arrays and strings, as such reusable abstract data types. Each abstract data type has an interface, the collection of operations that external code can perform on it. Any details beyond that interface are encapsulated, treated as internal to the type and of no concern to the rest of the program. Even basic things like numbers can be thought of as abstract data type whose interface allows us to add them, multiply them, compare them, and so on. In fact, the fixation on single objects as the main unit of organization in classical object-oriented programming is somewhat unfortunate since useful pieces of functionality often involve a group of different object classes working closely together. Methods. In JavaScript, methods are nothing more than properties that hold function values. This is a simple method. Typically, a method needs to do something with the object on which it was called. When a function is called on a method, looked up as a property and immediately called as an object.method, the binding called this in its body automatically points at the object on which it was called. You can think of this as an extra parameter that is passed to the function in a different way than other regular parameters. If you want to provide it explicitly, you can use a function's call method which takes this value as its first argument and treats further arguments as normal parameters. Since each function has its own this binding, whose value depends on the way it is called, you cannot refer to the this of the wrapping scope in a regular function defined with the function keyword. Arrow functions are different. They do not bind their own this, but can see the this binding of the scope around them. Thus, you can do something like the following code, which refers this from inside a local function. A property like findArray is an object expression and is a shorthand way of defining a method. It creates a property called find and gives it a function as its value. If I had written the argument to some using the function keyword, this code wouldn't work. Prototypes. One way to create a rabbit object with a speak method would be to create a helper function that has a rabbit type as its parameter and returns an object holding that as its type property, and our speak function as its speak property. All rabbits share that same method, especially for types with many methods. It would be nice if there were a way to keep a types method in a single place rather than adding them to each object individually. In JavaScript, prototypes are the way to do that. Objects can be linked to other objects to magically get all the properties that object has. Plain old objects created with bracket notation are linked to an object called object.prototype. It looks like we just pulled a property out of an empty object, but in fact toString is a method stored in object.prototype, meaning it is available to most objects. When an object gets a request for a property that it doesn't have, its prototype will be searched for the property. If it doesn't have it, the prototype's prototype is searched, and so on until an object without prototype is reached. Object.prototype is such an object. As you'd guessed, object.getPrototypeOf returns the prototype of an object. Many objects don't have object.prototype as their prototype, but instead have another object that provides a different set of default properties. Functions derived from function.prototype and arrays derived from array.prototype. Such a prototype object will itself have a prototype, often object.prototype, so that it still indirectly provides methods like toString. You can use object.create to create an object with a specific prototype. The proto-rabbit acts as a container for the properties shared by all rabbits. An individual rabbit object, like the black rabbit, contains properties that apply only to itself, in this case its type, and derives shared properties from its prototype. Classes. JavaScript's prototype system can be interpreted as a somewhat free-form take on an abstract data type or classes. A class defines the shape of a type of object, what methods and properties it has. Such an object is called an instance of the class. Prototypes are useful for defining properties for which all instances of a class share the same value. Properties that differ per instance, such as our rabbit's type property, need to be stored directly in the objects themselves. To create an instance of a given class, you have to make an object that derives from the proper prototype, but you also have to make sure it has the properties that instances of this class are supposed to have. This is what a constructor function does. JavaScript's class notation makes it easier to define this type of function along with a prototype object. The class keyword starts a class declaration, which allows us to define a constructor and a set of methods together. Any number of methods may be written inside the declaration braces. This code has the effect of defining a binding called rabbit, which holds a function that runs the code in constructor and has a prototype property that holds the speak method. This function cannot be called like a normal function. Constructors in JavaScript are called by putting keywords new in front of them. Doing so creates a fetch instance object whose prototype is the object from the function's prototype property. Then runs the function with this bound to the new object and finally returns the object. In fact, class was only introduced in the 2015 edition of JavaScript. Any function can be used as a constructor, and before 2015, the way to define a class was to write a regular function and then manipulate its prototype property. For this reason, all non-arrow functions start with a prototype property holding an empty object. By convention, the names of constructors are capitalized so that they can easily be distinguished from other functions. It is also important to understand the distinction between the way a prototype is associated with a constructor through its prototype property and the way objects have a prototype, which can be found at object.getPrototypeOf. The actual prototype of a constructor is function.prototype, since constructors are functions. The constructor function's prototype property holds the prototype used for instances created through it. Constructors will typically add some per instance properties to this. It is also possible to declare properties directly in the class declaration. Unlike methods, such properties are added to the instance objects and not the prototype. Like function, class can be used both in statements and in expressions. When used as an expression, it doesn't define a binding, but just produces the constructor as a value. You are allowed to omit the class name in a class expression. Private properties. It is common for classes to define some properties and methods for internal use that are not part of their interface. These are called private properties as opposed to public ones, which are part of the object's external interface. To declare a private method, put a # in front of its name. Such methods can be called only from inside the class declaration that defines them. When a class does not declare a constructor, it will automatically get an empty one. If you try and call #getSecrets from outside the class, you get an error. Its existence is entirely hidden inside the class declaration. To use private instance properties, you must declare them. Regular properties can be created by just assigning to them, but private properties must be declared in the case declaration to be available at all. This class implements an appliance for getting a random whole number below a given maximum number. It has only one public property, getNumber. Overriding derived properties. When you add a property to an object, whether it is present in the prototype or not, the property is added to the object itself. If there was already a property with the same name in the prototype, the property will no longer affect the object. It is now hidden behind the object's own property. The following diagram sketches a situation after this code has run. The rabbit and object prototypes lie behind killer rabbit as a kind of backdrop where properties that are not found in the object itself can be looked up. Overwriting properties that exist in a prototype can be a useful thing to do. As the rabbit teeth example shows, overriding can be used to express exceptional properties in instances of a more generic class of objects, while letting the non-exceptional objects take a standard value from their prototype. Overriding is also used to give the standard function and array prototypes a different toString method than the basic object prototype. Calling toString on an array gives a result similar to calling join on it. It puts commas between the values in the array. Directly calling object.prototype.toString with an array produces a different string. That function doesn't know about arrays, so it simply puts the word object and the name of the type between square brackets. Maps. We saw the word map used in the previous chapter for an operation that transforms a data structure by applying a function to its elements. Confusing as it is, in programming the same word is used for a related but rather different thing. A map, noun, is a data structure that associates values, the keys, with other values. For instance, you might want to map names to ages. It is possible to use objects for this. Here's the object property's name. Here, the object property names are the people's names and the property values are their ages. But we certainly didn't list anybody named toString in our map. Yet because plain objects derive from object.prototype, it looks like the property is there. For this reason, using plain objects as maps is dangerous. There are several possible ways to avoid this problem. First, you can create objects with no prototype. If you pass null to object.create, the resulting object will not derive from object.prototype and can be safely used as a map. Object property names must be strings. If you need a map whose keys can't easily be converted to strings, such as objects, you cannot use an object as your map. Fortunately, JavaScript comes with a class called map that is written for this exact purpose. It stores a mapping and allows any type of keys. The methods set, get, and has are part of the interface of the map object. Writing a data structure that can quickly update and search a large set of values isn't easy, but we don't have to worry about that. Someone else did it for us, and we can go through this simple interface to use their work. If you don't have a plain object that you need to treat as a map for some reason, it is useful to know that object.keys returns only an object's own keys, not those in the prototype. As an alternative to the in operator, you can use the object.hasOwn function, which ignores the object's prototype. Polymorphism. When you call the string function, which converts a value to a string on an object, it will call the toString method on the object to try to create a meaningful string from it. I mentioned that some of the standard prototypes define their own version of toString so that they can create a string that contains more useful information than object-object. You can also do that yourself. This is a simple instance of a powerful idea. When a piece of code is written to work with objects that have a certain interface, in this case, a toString method, any kind of object that happens to support this interface can be plugged into the code and will be able to work with it. This technique is called polymorphism. Polymorphic code can work with values on different shapes as long as they support the interface it expects. An example of a widely used interface is that of array-like objects that have a length property holding a number and numbered properties for each of their elements. Both arrays and strings support this interface, as do various other objects, some of which we'll see later in the chapters about the browser. Our implementation of for each from chapter 5 works on anything that provides this interface. In fact, so does array.prototype.forEach. Getters, setters, and statistics. Interfaces often contain plain properties, not just methods. For example, map objects have a size property that tells you how many keys are stored in them. It is not necessary for such an object to compute and store such a property directly in the instance. Even properties that are accessed directly may hide a method call. Such methods are called getters and are defined by writing get in front of the method name in an object expression or class declaration. Whenever someone reads from this object size property, the associated method is called. You can do a similar thing when a property is written to using a setter. The temperature class allows you to read and write temperature in either degrees Celsius or degrees Fahrenheit, but internally it stores only Celsius and automatically converts to and from Celsius in the Fahrenheit getter and setter. Sometimes you want to attach some property directly to your constructor function rather than to the prototype. Such methods won't have access to a class instance, but can, for example, be used to provide additional ways to create instances. Inside a class declaration, methods or properties that have static written before the name are stored on the constructor. For example, the temperature class allows you to write temperature.fromFahrenheit 100 to create a temperature using degrees Fahrenheit. Symbols. As mentioned in Chapter 4, that a for-of loop can loop over several kinds of data structures. This is another case of polymorphism. Such loops expect the data structure to expose a specific interface, which arrays and strings do. And we can also add this interface to our own objects. But before we can do that, we need to briefly take a look at the symbol type. It is possible for multiple interfaces to use the same property name for different things. For example, on array-like objects, length refers to the number of elements in the collection. But an object interface describes a hiking route could use length to provide the length of the route in meters. It would not be possible for an object to conform to both of these interfaces. An object trying to be a route and array-like, maybe to enumerate its waypoints, is somewhat far-fetched, and this kind of problem isn't that common in practice. For things like the iteration protocol, though, the language designers needed a type of property that really doesn't conflict with any others. So in 2015, symbols were added to the language. Most properties, including all that we have seen so far, are named with strings, but it is also possible to use symbols as property names. Symbols are created with the symbol function. Unlike strings, newly created symbols are unique. You cannot create the same symbol twice. The string you pass to symbol is included when you convert it to a string and can make it easier to recognize a symbol when, for example, showing it in the console. But it has no meaning beyond that. Multiple symbols may have the same name. Being both unique and usable as property names makes symbols suitable for defining interfaces that can peaceably live alongside other properties, no matter what their names are. It is possible to include symbol properties in object expressions and classes by using square brackets around the property name. That causes the expression between the brackets to be evaluated to produce the property name, analogous to the square bracket property access notation. The iterator interface. The object given to a for-of loop is expected to be iterable. This means that it has a method named with the symbol.iterator symbol, a symbol value defined by the language stored as a property of the symbol function. When called, that method should return an object that provides a second interface, iterator. This is the actual thing that iterates. It has a next method that returns the next result. That result should be an object with a value property that provides the next value, if there is one, and a done property, which should be true when there are no more results and false otherwise. Note that the next value and done property names are plain strings, not symbols. Only symbol.iterator, which is likely to be added to a lot of different objects, is an actual symbol. We can directly use this interface ourselves. Let's implement an iterable data structure similar to the linked list from the exercise in Chapter 4. We'll write the list as a class this time. Note that this is a static method, points at the constructor of the class, not an instance. There is no instance around when a static method is called. Iterating over a list should return all the list's elements from start to end. We'll write a separate class for the iterator. The class tracks the progress of iterating through the list by updating its list property to move to the next list object whenever a value is returned and reports that it is done when the list is empty, null. Let's set up the list class to be iterable. Throughout this book, I'll occasionally use after-the-fact prototype manipulation to add methods to classes so that the individual pieces of code remain small and self-contained. In a regular program, where there's no need to split the code into small pieces, you declare these methods directly in the class instead. We can now loop over a list with for-of. The spread syntax in array notation and function calls works similarly with any iterable object. For example, you can use the spread syntax value to create an array containing the elements in an arbitrary iterable object. Inheritance. Imagine we need a list type much like the list class we saw before, but because we'll be asking for its length all the time, we don't want to have to scan through its rest every time. Instead, we want to store the length in every instance of the efficient access. JavaScript's prototype system makes it possible to create a new class, much like the old class, but with new definitions for some of its properties. The prototype for the new class derives from the old prototype, but adds a new definition for, say, the length getter. In object-oriented programming terms, this is called inheritance. The new class inherits properties and behaviors from the old class. The use of the word extends indicates that this class shouldn't be directly based on the default object prototype, but on some other class. This is called the superclass. The derived class is the subclass. To initialize a length list instance, the constructor calls the constructor of its superclass through the super keyword. This is necessary because this new object is to behave roughly like a list. It is going to need the instance properties that lists have. The constructor then stores the list's length in a private property. If we had written this.length there, the class's own getter would have been called, which doesn't work yet since #length hasn't been filled in yet. We can use super.something to call methods and getters on the superclass's prototype, which is often useful. Inheritance allows us to build slightly different data types from existing data types with relatively little work. It is a fundamental part of the object-oriented tradition alongside encapsulation and polymorphism. But while the latter two are now generally regarded as wonderful ideas, inheritance is more controversial. Whereas encapsulation and polymorphism can be used to separate pieces of code from one another, reducing the tangledness of the overall program, inheritance fundamentally ties classes together, creating more tangle. When inheriting from a class, you usually have to know more about how it works than when simply using it. Inheritance can be a useful tool to make some types of programs more succinct, but it shouldn't be the first tool you reach for, and you probably shouldn't actively go looking for opportunities to construct class hierarchies, family trees of classes. The instanceof operator. It is occasionally useful to know whether an object was derived from the specific class. For this, JavaScript provides a binary operator called instanceof. The operator will look through the inherited types, so a length list is an instance of list. The operator can also be applied to standard constructors like array. Almost every object is an instance of object. Summary. Objects do more than just hold their own properties. They have prototypes which are other objects. They'll act as if they have properties, but they don't have it as long as their prototype has that property. Simple objects have object.prototype as their prototype. Constructors, which are functions whose names usually start with a capital letter, can be used with the new operator to create new objects. The new object's prototype will be the object found in the prototype property of the constructor. You can make good use of this by putting the properties that all values of a given type share into their prototype. There's a class notation that provides a clear way to define a constructor and its prototype. You can define getters and setters to secretly call methods every time an object's property is accessed. Static methods are methods stored in a class's constructor rather than its prototype. The instanceof operator can, given an object and a constructor, tell you whether that object is an instance of that constructor. One useful thing to do with objects is to specify an interface for them and tell everybody that they're supposed to talk to your object only through that interface. The rest of the details that make up your object are now encapsulated, hidden behind the interface. You can use private properties to hide a part of your object from the outside world. More than one type may implement the same interface. Code written to use an interface automatically knows how to work with any number of different objects that provide that interface. This is called polymorphism. When implementing multiple classes that differ only in some details, it can be helpful to write the new class as subclasses of an existing class, inheriting part of its behavior. Exercises. A vector type. Write a class vec that represents a vector in two-dimensional space. It takes x and y parameters, numbers, and it saves to properties of the same name. Given the vec prototype, two methods, plus and minus, that take another vector as a parameter and return a new vector that has a sum or difference of the two vectors, this and the parameter x and y values. Add a getter property length to the prototype that computes the length of the vector, that is, the distance to the point xy from the origin 0, 0. Groups. The standard JavaScript environment provides another data structure called set. Like an instance of map, a set holds a collection of values. Unlike map, it does not associate other values with those. It just tracks which values are part of the set. A value can be part of a set only once. Adding it again doesn't have any effect. Write a class called group since set is already taken. Like set, it has add, delete, and has methods. Its constructor creates an empty group. Add adds a value to the group, but only if it already isn't a member. Delete removes its argument from the group if it was a member, and has returns a Boolean value indicating whether its argument is a member of the group. Use the triple equals operator or something equivalent such as index_of to determine whether two values are the same. Give the class a static from method that takes an iterable object as its argument and creates a group that contains all the values produced by iterating over it. Iterable groups. Make the group class from the previous exercise iterable. Refer to the section about the iterator interface earlier in the chapter if you aren't clear on the exact form of the interface anymore. If you use an array to represent the group's members, don't just return the iterator created by calling the symbol.iterator method in the array. That would work, but it defeats the purpose of this exercise. It is okay if your iterator behaves strangely when the group is modified during iteration.